Secondly, the HK effect. So this is the expansion as you move out into the corners of the color space to account for that additional perceived brightness value. So the way the color nits measurement works, it uses standard equipment. So you would measure as you would normally using a calibrated spectroradiometer each channel, red, green, or blue, as well as the white. And then you also have to take a standard color gamut display, which we're right now considering to use a white LED plus the ag phosphor. So the inputs to this model, or this measurement, are very similar to how you would normally measure a display. Then you make two calculations. One is you correct for this luminosity efficiency factor, and I'll go through that. And the second is this HK effect, which is a known set of calculations. So here's the one. So just taking this one step at a time. So model inputs are based on standard display measurements. So we normally get this white number. That's the number that most people report as a white nit value. So with those numbers for red, green, and blue, and for white, those are then fed into a set of calculations. I won't take you through this at this time of the evening, but I've included it here just for folks to digest after the talk, and happy to discuss them further. We will also have a white paper put out to further the discussion of this proposal. But basically, what we're doing here is as I said, we're taking a standard measurement of the spectra. We're normalizing that spectra to so both the standard and the white color gamut. And we're computing the photometric energy, or the relative luminance, for each. And we do that both for the white color gamut and the standard color gamut. And then we divide out that photometric piece to account for, so that we have a photon representation of the brightness. So this is just showing you the examples of the SCG, which is the standard, and the WCG, which is the white color spectrum. And then you multiply that on the left in step 3 by the photopic, and you end up with two curves. So in this example, the ratio of the standard color gamut will be higher. There are cases, by the way, where the quantum dot case could be actually higher illuminance. For example, if I take the red in, if I can move that red in and then bring closer to the 555, I can actually change that over, let's say, the ag phosphor. So I think that's important to note, because if you're making a display that's going to peak for luminance that you measure, this is not going to exaggerate the color. You'll in fact get a lower score here for color in that case. Again, we're talking about color brightness around the edges of the triangle as opposed to the center point for white. So in that sense, we believe it's a fair measure. So the HK factor, this is even more equations, so I'm not going to take you through it. This is well discussed, and we have the slides. But basically, you have to convert XY into the CIE lab coordinates, and then run your calculations for lightness, chroma, and hue. But what comes out of this is basically a luminance value that accounts for this HK effect. So if you remember that contour that we talked about, that contour is represented in the first term. So this slide sort of summarizes the calculation. So we have two parts. The HK effect, which is this expansion of perceived brightness as you go to the edges of the triangle. And then the second part is just counting photons, not nits. And right now in the calculations that we've put together, we assume it's a 1 nit D6 line for white. These, of course, can be scaled appropriately after. So if you have a value of, let's say, some number of nits, you can just multiply the ratios, the factors, to get the effect, or the brightness enhancement that you would perceive. This sort of ran on, looks like the last sentence. numbers sort of ran into each other, but this is just a sample calculation which you have in the slides. It should look better in the slides that you have. But in this example on the left, we have a white color gamut display, which has a CNITS value if I sum up the RGB components of 2.23. And the standard color gamut on the right would be, in this calculation, 1.74. So that ratio gives you about a 30% advantage of color that we believe is a good estimate for what your eye will see. And if you're interested in actually seeing this effect, I would encourage you to purchase one of these Philips monitors, and we have them all around our company. And a lot of folks, when they buy monitors, they're set to some standard brightness, and that's, again, by measurement. But what we're finding is everyone is dialing these things down because the brightness that they're actually seeing is too high. So this is just an example, but so in this case, for this example, we show that there's a 30% brightness advantage for color for the white color. So our motivation here, I hope I've explained, is to consider a way of capturing this color brightness advantage that we see and coming up with a measure of that. Whether at the end of the day we call it color nits is up for discussion. We don't want to confuse folks if this becomes a true standard. Maybe it's a color index, maybe it's a color ratio or factor, but there's definitely something there that's not represented today. And as we all buy TVs and stuff online, it's going to be hard to convince a consumer to go buy this type of device if all they have is an sRGB display to look at when they're shopping, right? So that's part of the motivation. The other thing is another example, which I don't have time to go into, but is this notion of brightness perception as a function of ambient. So that's another one where the common nits number doesn't really help you with, doesn't really tell you what the color looks like under different ambient conditions. White, if it's 200 nits in white, depending if it's a bright room or a dark room, there is there's this light adaptation of vision that will change the perceived brightness for white. And the perceived brightness of color content is not affected by this. We believe that this metric would help us further communicate that. So this slide is based on some feedback we actually got at SID. We had some questions come in from the press, so I just wanted to address them. But right now, this measurement is, or calculation is derived from standard white point movements in RGB and white point chromaticities that are normally accessible to the field. We don't require any test patterns, any special test patterns to do this measurement. And it's unaffected by gamma coding, as it only depends on the current methodology for luminance and CV measurement. And really, we want to start a conversation here. So we encourage those that are in the business of providing these monitor calibration or display calibration applications to incorporate color nits into their respective applications. So we're looking for folks that would like to pursue this further. And that's really it. So really 3 points that I want you to go home with. One is that QD TVs are currently associated with best-in-class viewing performance, and that adoption is accelerating. We believe current measurements of luminance and chromaticity do not capture all the benefits of these displays, so we need to catch up. And we propose color nits as a way to help capture that value. So one more time, this is just a proposed metric. It's something that requires a lot more work, but it's something that we'd like to work with people with in the industry. Perhaps there's even similar cases on projectors and other parts of the display industry where this has been maybe looked at, but I'd be very interested in talking to you guys about that. Thank you. Questions? Can you hear you?
In your world, in 2D world, narrowband looks like it's 20, 30, 40 nanometers. In RGB laser land, it's a whole lot narrower than that. Would you expect, what would you expect if you use this metrology approach with a very narrow band, let's say closer to fully saturated Rec 2020? Would you expect a much bigger effect or the same?
I would expect the HT effect to be, which is the dominant factor, by the way, in this measurement, to be probably the highest. It should be the highest.
And
but I haven't run the calculation, but it's something we should do.
That's in the paper that you downloaded, so it could be applied to
yes.
narrowband RGB.
Absolutely.
And then
it's not specific to QDs. In fact, the more narrower you are, you get the HT effect's going to go through the roof. And yeah, and also the other factor should also the other factor is more of a normalizing factor for photons, so that should be even.
okay, thank you.
So, have you thought about taking this to the ICDM now? Do you know about them a little bit more?
I'm very interested in talking to this. I think we should have a conversation with the intentions.
I had a question. Do you see color nits as more of a useful comparative metric for consumers to help inform their purchasing decisions, or are you actually proposing color nits as a target or a metric for actual display calibration?
That's a good question. I'm not sure. Yeah. I think it's more the former than the latter. You know, I don't have, in terms of a calibrated display, I think there are parts, in making a wide color gamut display, you know, there are some, some companies do it very well, some don't, and I think a lot of that comes down to other aspects of making a good display, and I think, I'm not sure there are any calibration problems today for wide color gamut. The thing that we're seeing is that there's this specsmanship that's going on in the industry, and if you're competing against the ICOS for, it's hard to sell the benefit. It can be hard to sell the benefit of something that's really there. In case you have the TVs, and you're looking at them side by side, and you're very informed. So I think to answer your question, it's more the former than the latter. But who knows? I mean,
that makes perfect sense. I was actually hoping it was that.
Yeah.
Because I think the latter's going to be real hard to convince people of.
Yeah.
Okay. Thank you very much. And thank you. Last but certainly not least, Donahue Lee from LG Display is going to talk about some more of the challenging future metrology issues. Yep. It's okay.
Okay, my name is Donahue Lee, and before I begin, I would like to announce two things. One of that is the good news, and the other is a bad one. The good news is that my talk is the final one of today. And bad news is maybe my talk is gonna a little bit boring, but I'll do my best to make it valuable to sit on this chair. And also I try to as quick as I can. And I actually work in LG Display to enhance the image quality for the future display things. For example, transparent display, and that's what I'm focusing on these days. And also for the virtual reality, and the other is maybe the part of them is HDR. So I'm really interested in to make a new metrology, because in order to enhance the image quality of the new function of the displays, we need to know how to define the function of the new technology. So part of my job is to make a new measurement method, and that's why I'm working with Joe Misari in ICDN, and also I'm working for IEC and ISO. So most of the talk of my presentation is therefore relating with the three things. One of them is transparent and HDR and real. So this is